All right, here we are again. So here's what we're going to do today. Well, first things first, we're done with the first three chapters. The midterm is on chapters 1 through 3 only. So that means it's time for the sample midterm, which is on Moodle. Let's go look at it.
Recording.
All right, let's see. Hold on. All right, so let's see, where did I put it? There we go, sample midterm number 1. So again, this is for just 1 through 3. It's very similar to the problem sets that we've been doing, but it gives us a chance to get a lot more extra practice before we do the real thing. And so you can see there's a group of short questions here that we haven't really done before, but you'll see that you shouldn't have any trouble with them. They're basically trying to find out if you understand basic definitions and concepts without doing actual problems. But every one of these is somewhere in your slides. If you're not sure, if you've forgotten, you can just go back and look through your slides or your notes, or even watch the videos again. And then these problems, as you can see, should look very familiar because they're pretty much what we've been doing all this time. So it's a fairly long document, but it's a long class. And so the first thing we'll do next week is work on this sample midterm. And then I'll post the answers, of course. And then when that's done, what I can do is actually post the midterm online, on Moodle that is. And then I'll give you about a week or so to get it done. But just keep in mind, this test that you're about to take, or will take, was meant to be done in a classroom setting in less than 2 hours. So it's not going to take you a week, but you can have it anyway because, you might have other things going on. You might have other tests to deal with. So just to make sure there's no rush, you can have a week, and then you can spend that whole week reviewing all of your materials. And then when you're done, you can write up your answers. Most likely you'll do them by hand. But no, if you're a good typist, you can do that too in Word. But the bottom line is, in order to get it back to me, what most people ended up doing in the past was they took pictures of it with their cell phones, and then they emailed them back to me. Although I must say, there do exist now some nice scanning software or apps that you can buy or download for your iPhone. There's one in particular, this thing called Genius Scan, which a lot of people have told me they had good success with. And so if you download this app on your iPhone, apparently all you have to do is hold your phone over the document and it turns it into a PDF file, which looks very clear and it's easy to read. And then you can just email it back to me. You don't have to do this, but I think it might be a good idea. Look at this, 4.9 out of 5. And I did get a few last semester and they did look very good, I must say. So this is in effect a virtual scanner. If you have a printer in your house, on the other hand, it probably has a physical scanner in it anyway, and you can feel free to use that instead if you want to, or else use this scanner. And if you don't want to do any of those things, you can just use the old camera, which the thing about the camera, though, is if you're going to use the camera, make sure that you can read the documents yourself before you send them to me, because, I did have a few issues with the pictures because either they were too small to read or there was a lot of glare. That kind of thing can really throw off a picture of a document. Whereas with the scanner, it should be pretty clear no matter what kind of lighting conditions you have. So I'll leave it up to you, but when you're done with it, you can send it to my purchase account. The reason why I would like you to do it with my purchase account is because my Gmail account is, let's face it, I get a lot of Gmails there or emails there. And if you send it to my purchase account, it's just easier for me to keep them all together in one place. And then I don't have to search around all over the place to find them. So that's really, that can be a real problem. When I've got a bunch of classes going on at once and I'm getting a bunch of emails, and some of them go in the junk box and some of them never get here, and it's kind of a headache. So just to keep the aggravation down to a minimum, I'd like to ask you to send them to my purchase Gmail or email. You keep saying Gmail, which is just alananderson.at-purchase.edu, which is in the syllabus, by the way. Okay, so let's see, maybe I could go open that up right now. Now, if you forget and send it to my Gmail account, that's fine, but I would prefer that you send it here. Okay. Oh, I forgot about this. Yeah, all these high levels of, oh my God. I guess they're afraid that Russian hackers will read my purchase emails. Okay, here it is. Yeah, so it's, where's my information here? No. Well, all right. Oh, there. No, all right. This is what I wanted you to see. alan.anderson@purchase.edu. So please send it there. Just like I said, because this way it'll all be together in one convenient location. And that will make it harder for it to get lost, because I know from experience that with such a large group, some of them will not arrive in my inbox at all, and some of them will go in the junk box. Some of them will be returned to you because the file sizes are too big. So if that happens, we have to figure out something else, like use, what is that thing, Google Drive. So, we'll work that out. But one thing you can do, though, is if the files are very large, rather than trying to send them all on a single email, you could send them as a series of emails. If you do that, put in the put in the subject line something like, John Smith's exam part 1 or something along those lines, so I know that there's meant to be more than one. Oh, and one more thing. Now, this is something that you don't think about, and I'm not sure if this is even feasible, but if it's possible, when you save your files and you send them off to me, if you could edit the name of the file to include your name, it makes it easier for me to gather up all the exams and save them. So in other words, if the file name is just exam or something like that, well, then I don't know who you are. I mean, I know from your email, but once I download it, it can get lost and separated. So ideally, you would have in the title of your file your own name, and that just makes it easier for me to organize the information. And again, if you forget, it's okay, I'll figure it out. But the more people who do that, the quicker it'll be for me to get them all together and then start looking at them. All right, so all right, that should be enough information for now. We can review this again next week after we go over the sample midterm. Okay, now the next thing we want to do, and this is something I'd hoped to do earlier in the semester, but we kind of got involved with other things. Somewhere along the way, I discovered this extremely interesting series on YouTube. I guess it was YouTube. And, oh, here we go. I guess I lost my Moodle. Oh no, here it is. I found this extremely interesting series on, it's a multi-part series on YouTube about imaginary numbers and their applications. And, in this series, they're going to talk about not just imaginary numbers, but other things as well that are directly relevant to what we've been doing. Now you can see it's broken up into 9 parts. Each one is about 3 or 4 minutes long. So it's going to take a good half an hour to work through all this, but I think that with all the work we've done so far, I think we kind of deserve a little break here. And I really think you'll enjoy this series very much. So I'd like to start today by showing you this 9-part series about imaginary numbers, which will make you think a lot more about what they're for and what they're used for and how important they are. But also it introduces a lot of other very important concepts, which I think you'll find extremely interesting. And then when we're done with all that, we can get back into chapter 4, which we started the other day. And this is our discussion about, let's get this thing open. exponential logarithmic functions, which we started, but we of course did not finish. We have quite a few interesting applications to look at. And if we finish this, maybe we'll take a peek at chapter 5, but I don't know if that's going to happen. So in the meantime, though, why don't we start today by watching these videos, and then we'll go over them. We'll maybe discuss some of the ideas that we saw in there, and then we can, with the rest of the time, we can finish 4 maybe, or at least get a lot of it done, and possibly take a quick peek at 5. Okay, so let's do that. Here we go. All right, so as usual, I will send you the link by the chat room, and then you can watch it on your computer, because the sound will not be good if you try to watch it on mine. So this is part 1 of Imaginary Numbers Are Real. Now, 6 months ago, if somebody told you you would find this topic exciting, you probably would have thought they were crazy. But when you see these, you'll say, wow, this is really interesting. All right, so hold on, let me send this off to you. The Notes app also has a scanner. Oh, okay. Well, I'm glad you mentioned that, because I did not know that. Okay, does everyone see that? The Notes app also has a scanner. So yeah, there's others too besides Genius Scan. So whatever you need to do, but scanners are always a better choice than using the camera, just because they're designed to do this kind of thing. The camera is not. It's really not meant to take pictures of documents. It's really meant to take pictures of anything else. And it works okay with documents, but you just have to be careful with it. All right, anyway, here we go. So this is the link. Why don't we get started and watch this? And I think you'll agree, even after part 1, wow, this is exciting stuff. Okay, all right, so let's do this. All right. Well, I think you see what I mean. It's an extremely interesting series, and he takes it to a lot of different directions that you might not expect. So it's kind of funny how Carl Gauss, who's one of the great mathematicians of all time, was so upset about the name imaginary. I guess he figured it's just going to confuse people, but I don't know. It's just a name, but it wasn't. He wasn't too happy about it. So but you can see what the problem is. It's a very bizarre idea. And but yet at the same time, though, it has to be the case that these things exist because otherwise a lot of the results that we know in math would fall apart. So it's an important extension of the real number system, but it's only been very recently that they were accepted, as they said in the video. Because I mean, imagine if initially in the early years of the human race, negative numbers were like couldn't even begin to be thought of. So you can imagine that imaginary numbers would have been treated with far more skepticism when first they were thought of. So in other words, it was a much more strange concept than even negative numbers. But anyway, here we are today, and they're used all the time in engineering and in certain other disciplines. Um, but anyway, here comes part two. You just fire this off to you. All right, let's check this out. All right, so that it's getting more exciting every time, isn't it? So let me send out that new one. Number 3. We're going to find out what happened with Cardan's problem. All right, here we go. Excellent. So let's get started on that one. All right, it's time for number 4. There we go. Okay. Okay, so we're ready for 5. All right, check it out. Uh, okay. Well, it's getting more interesting all the time, isn't it? Here comes six. Okay. All right, here we go. It's time for part 7. Very good. Let's do this. Hmm. Okay, I think we're ready for 8. All right, so it looks like we're ready for the grand finale, part 9. Okay, here we go. Mm. Wow, how cool is that puzzle? Maybe if we go on Amazon, we can find one and we can buy it for ourselves. Who knows? It might be fun to play with that thing. But yes, it was quite an interesting series. I mean, who knew that imaginary numbers were so important and so interesting, and they had such a long and interesting history. You can see why mathematicians resisted them for so long, because it was still a very complex idea. I mean, really, you can't visualize what imaginary numbers look like, not really, but you can see how they're potentially so very useful in a lot of applications. Now, he mentioned several times the unit circle. Interestingly enough, we're going to actually introduce that in chapter 5, but for a very different reason, because in chapter 5, we're going to take a little bit of a detour into an area that you have probably not thought about for quite a long time, and that would be trigonometry. Yeah, trigonometry. There, I said it. Trigonometry, which means we'll be talking about sines and cosines and secants and all the rest, but not just yet. We're still not done with chapter 4, so let's carry on with that. And just remember, next week, our plan is to do the sample midterm so that we'll be ready to do the actual exam, midterm, that is. So right now, what we're going to do is get back into chapter 4, where we left off. And now you have your newfound appreciation for imaginary numbers. And in fact, it's funny too, sometimes you never know what this stuff can turn into. There's actually a t-shirt you can buy. It should be on the internet somewhere. This is for real math people though. Let me see if I can find it. Let's see here. No, that's not what I had in mind. Okay, see, this is math humor. You don't have to buy this shirt, but I think what they're trying to get here is I wish I could make that bigger. This is a math guy. Okay, you can tell right away. So this is 2 to the third is 8, sum pi. And it was delicious. So all the other math people will come up to you and say, hey, that's a cool t-shirt. Where can I get one of those? So if you're interested, 20 bucks. All right, no, but that's not the one I had in mind. There's another one that is making the rounds. I think this might be it. Oh, no. No, that's not it. Of course, you know what's going to happen. I'll be able to find everyone except the one I actually want. That's often how it works. All right. Well, then I'll just have to, okay, maybe I can. Oh, I think I found it. Woo-hoo. All right. So I'll have to blow this up quite a bit. So maybe you can see it. I hope you can. I and pi are having a conversation. And I is saying, be rational to pi. And pi is saying back to I, get real. It's math humor, okay? But if you see somebody wearing one of these, you know this person is a serious math individual, and they are this is what they live for, math, okay? So you never know. You might want to buy one of these, or suppose somebody gives it to you as a present, you'll wear it proudly because you do understand what this means. All right, so enough of that. That's enough of that fun stuff. Let's get back to chapter 4. And so we've been looking briefly at a logarithmic, and well, we're going to do logarithmic later on. We started with exponential functions. And remember, that simply means that we have an initial value, we have a base, which represents 1 plus the growth rate, and then we have an exponent. And this represents what we call an exponential function, which indicates that we have some variable which is growing very quickly. I did a very quick review of logs because we're going to need them very soon. And oh yeah, some applications. E, which we're going to need quite a bit of in this chapter, is 2.71828. And the log to base E, let's recall, is the so-called natural log, which is designated log x or lnx. E to the x is sometimes written exp of x. All right. So this is what an exponential function looks like. You can see it grows very slowly at first, and then it grows very quickly. And its domain is the entire real number line. The range, though, is everything from 0 up to infinity, not including the 0. You can see that this function will never quite touch the horizontal axis. If, on the other hand, we have a negative a, this one assumes that a is positive, by the way. If not, let's see if I can squeeze this in here. It'll look more like that. And then the domain is still all the reals, but the range will start with 0. Well, actually, it starts at negative infinity. It goes up to, but not quite reaches 0. All right. So in other words, these two are mirror images of each other. In both cases, though, 0 is not part of the function. All right. So we had some examples. Here's an example of a graph in Excel. And now for applications, we often find that we're restricted to the first quadrant because let's say, for example, we're trying to understand how quickly the value of a coin is growing or something like that. Then no negative numbers would make sense. So we'll start here and we'll focus all of our attention on the first quadrant. Okay. Now, of course, exponential growth means that something is growing very, very quickly. So this function is showing you that x is the exponent. And so that's why the growth is so rapid. Now, we did this example with a painting or two paintings, one which is growing at a linear rate and the other which is growing at an exponential rate. And we can see that, let's just look at the graph again. Initially, the growth rates are very similar, but after a while, the exponential growth, the orange one is exponential, by the way. And the blue one is linear growth. Okay, so, oh, by the way, let me save this real fast. Today's the 6th. Oh, so anyway, yes, so you can see the linear growth, it's pretty steady, but the exponential growth is growing at an increasing rate. In other words, the rate of growth is itself increasing. And so as time elapses, the spread between the two curves will continue to widen. And so that the exponentially growing painting eventually will be worth quite a bit more than the linearly growing painting. And then we saw some examples we saw for the growth rate. We had this case with the deer. In 2006, we had 80 deer. By 2012, there were 180 of them. How fast are they growing? Well, we're assuming that the growth rate is exponential. And based on that assumption, we rewrote this function in terms of time. And so you can see that what we're essentially doing is taking the ratio of the new population over the old population. That is actually the growth rate after 6 years. So to find the correct value, we raise this to the 1/6 power. And then we subtract 1, and we end up with 0.1447 or 14.47% growth per year. So The deer are growing at roughly 14.47% per year. The silver dollar. Yeah, that was a cool one because it starts at $1 in 1899. 120 years later, look how much it's worth, 37.42. And that's a lot. A lot of it is because it's collectible. Of course, it's an old coin. It's no longer being minted. It's made out of silver. And if it's in good condition, it could be worth an awful lot of money, especially if it was very rare when it was first minted. Ultimately, the values of these coins depends on their condition and their rarity. So here, this one is worth 37.42. And so we can figure out from those two numbers, the initial value and the final value, what the growth rate must have been during that period using the same setup. And that means roughly 7.1% per year is the value that your investment is growing at, which is not bad considering that, when you think about what you're getting in a savings account. And then by the way, just for the fun, why don't we take a look at what an 1899 silver dollar looks like? I think you'll be impressed. Oh yeah, look at that. This is the back, by the way. That's a beautiful coin. It's big. It's really big. It's a very heavy coin. It was worth $1 at the time. Now, according to this, it's only $2.79. So that tells me that, well, first of all, somebody polished it, and that always ruins the value of a historic coin. So you can get it. It's cheap. Let's try. Oh, look at this one. $4,000. So clearly this one is in better condition and has not been cleaned. And it also was probably more rare at the time it was issued. Okay, so here is your silver dollar. That one is worth about $4,000. Oh, micro O. That's what makes it so expensive. The O, which represents the mint that it came from, is smaller than the rest of the coins that were produced. So in other words, it's a rare coin. Okay, it's little things like that that can make it so much more valuable. Okay, and there's the back. All right, anyway, I thought you'd find that interesting. So let's go ahead. So we also did one more thing here, exponential functions. We used 2 points to solve for the equation. And we might remember that this is much more complicated than what we have to do with a linear equation, because we ultimately have to solve 2 equations at the same time. And so we went through all the steps and we discovered, how to do this. And then finally, we saved some applications for today. Okay. Now, here we're delving into a very applied area. We're looking at interest, specifically compound interest. So let's just have a quick review, a little bit of a primer on how interest works. So you know perfectly well, I guess, that when you put your money in the bank, they pay you interest. Not much, but they pay you interest. So how much do they pay you? Well, you'll go to the door of the bank and they'll have a sign that tells you what interest rate they're paying on their accounts. And with that information in hand, you should be able to figure out how much your account balance will be at a particular point in the future. So the way this works is the interest that you're going to earn. First of all, if you leave the money there long enough, 2 types of interest you'll earn 2 types of interest. The interest on the original amount you deposited, which is called principal, and then the interest on the interest as the account accumulates interest over time. All right, so in other words, let me just show you a quick example of that, just so you can get a feel for what that's all about. So let's just say, just to keep it simple, suppose that an investor deposits $1,000 in a bank account that pays a 5% rate of interest. Now, to keep it simple, we will assume that interest is credited to this account at the end of the year. Okay, so there's once a year, they put 5% in your account. That's not how it works in practice, but let's just say that that's what they're doing. How much will this account be worth in 2 years, assuming that no money is withdrawn or deposited during this time period. All right, so how does that work? Well, here's how it goes. At the end of the first year, the balance will be 1,000 times 1.05, which is 1,050. At the end of the second year, the balance will be, now here's where it gets interesting. If you notice this time I'm multiplying the now by the way, 1.05 is B in our formula from before. This is actually 1 plus the growth rate, or in this case, the interest rate. Okay, so that's why I'm multiplying it by 1.05. The 5% represents the interest that we're earning. The 1 represents the return of principal, which means, in other words, when we take the money back, they'll give us our original deposit back, plus a little bit more money, which is our interest. So at the end of the second year, when this second year starts, we don't have $1,000 in our account, we have $1,050. To figure out how much we have at the end of the year, we multiply that by 1 plus the rate of interest. So then we have 1,102.50. Now, this is where it gets interesting. That means that of this 1102.50, 1,000 is the original principal. 102.50 is the interest. Okay, now you might say, what's so interesting about that? Well, let's take a look at the interest now. Now, of the 102.50, 100 is the simple interest. Why do I know that? Because this is calculated as 1,000 times 5% times 2 years. In fact, why don't I write out the formula here? Principal times rate times time. And therefore, I have 1,000 times 5% times 2, which is only $100. Well, where did the rest come from? Good question. The remaining interest of 250 is known as compound interest. Compound interest. This comes from the interest earned on the $50 interest at the end of the first year. All right, so in other words, if you remember, at the end of year 1, we had $1,050 in our account, of which 1,000 is principal and the rest is interest. In fact, why don't I make a note of that here? So then at the end of the second year, you're getting paid interest on both this original principal plus this $50. So that's the part that generates the so-called compound interest. So if you look at this 1102.50, you're getting $50 a year in simple interest. The rest is the compound interest. Okay, so in other words, and this is the key detail, the simple interest will be $50 per year. The compound interest equals total interest minus simple interest. So you might say, well, you know what, that's only 250. And that doesn't sound like a lot of money, but you know what, after enough years go by, eventually you'll end up with more compound interest than simple interest. In fact, if you want to see how this works, we can go into Excel and put together a quick spreadsheet where we see exactly what will happen in the future. So you could have oh, I need principal. So let's do that right now. I don't know if anyone here uses Excel. If you don't, you should. All right, so let's see what we can do here. Let's see, that's going to be okay. So one more thing. Oh, I did something wrong. Oh, I know what's wrong. Okay, so no. All right, so I've set it up so that, oh no, something's still wrong. Hold on. Hmm. Oh, yeah, I don't know what the problem was. Anyway, so, all right, so let's make this a little neater. Dollars and cents. All right, so you can see what's happening here up to, let's say, 6 years. Oh, let's do 5 years. All right, and we can stretch this out as far as we want. But what's happening is that every year, the balance is going up, but it's going up by more than $50. And so the total interest is going up. The simple interest is never changing, but what's happening to the compound interest? It's continuously going up because each time it's based on a larger value. Okay, so in other words, this is the new interest is being based on a progressively larger balance. So there will come a time when the compound interest is more than the simple interest. In fact, if we drag this down far enough, you'll see that this happens in year, right about here, they're the same, roughly the same. And then after that, the compound interest grows. So if you were to plot, let's say, the year against the interest. In fact, we could probably do all three of them. Total, simple, and compound interest. See if we can squeeze these onto a nice graph. All right, I have confidence in Excel. I'm going to try to find a nice graph that will illustrate this. All right, let's see what we can do. Okay, that should do it. It's not a very pretty graph, but it will do the job. We could spend, we could make it prettier if we want to. There's no need for that. We don't want to waste all day here. But let's just see what this is all about. So basically, in a nutshell, what we're seeing here is that the blue line is the total interest. You see, well, it's not easy to see it, but it is growing not at a linear rate, but it's growing at an increasing rate. It will continue to get steeper as time goes by. The orange is the simple interest. It never changes. It's always $50 a year. And the compound interest is always the difference between the two of them. So as we saw earlier, right around year 14 is when the compound and the simple interest are equal. After that, the compound interest will always be more than the simple interest. So that's why this is so important. So this is why, by the way, I bet that one is nice, isn't it? Why, if you're saving for retirement, for example, it's very important to start early, because the amount of interest you'll get will be a lot higher if you start at a younger age than an older age with your savings. I'll just label that interest. So those are the three basic types. Again, the total, simple, and finally compound. Yes, the compound interest. Well, the compound interest will only increase exponentially under certain conditions, but it's growing very quickly. Maybe not as quickly as exponentially, but there is a special case where it will grow that fast, which we will see in a few minutes. But yes, you're absolutely right. Right now, with this particular case, it's growing almost exponentially. And so because of that, the compound and the total are both growing exponentially or nearly exponentially. The simple is actually just staying at a constant amount, $50 every year. That's exactly right. So anyway, I wanted to go through all that because I don't want to assume that you've already been exposed to this before. I don't know, for all I know, you may not have ever even had a bank account just yet because you have no money to save. But once you do, this is all going to become very, very important. You'll have to understand what the bank is doing and how they're figuring out how much interest they owe you. And so this will help you with your planning, that's for sure. It doesn't help you make more money, but it helps you earn more money in your investments, that's for sure. All right, now let me just quickly save this. I'm going to actually post this on Moodle just in case anyone wants to download it and look at it, especially if you're trying to learn Excel, which you really should. No matter what you're studying, it's hard to imagine an area that wouldn't benefit from knowing some Excel, even if you just use it to plan your own personal finances. All right, yeah, so I'll put that up there later on, so you can go through and see what I did. You can see now I do this all the time, so that's why it takes a while to learn how to do this, but once you do, it's really a very helpful tool. And of course, a lot of functions that we'll be using today are built into Excel as well. You can use any kind of algebraic expression in here. And this is where it really pays for itself. If you only need one number, that's fine. But if you need a group of numbers, like if I want to see all the different compound interests all at the same time, it would take me forever to do this with a calculator. So instead, I do it in Excel, and I can see them all together and understand the relationships between these two, the three. All right. So I thought that was a worthwhile detour to take. All right, let's see. Now, here's a formula. Now, all right, let me add one more detail here. All right. So in our example, we assumed that interest is only paid once per year. Okay, 5% once per year. Okay, in practice, the interest can be paid more frequently. For example, the bank could pay 2.5% twice per year instead of 5% once per year. Okay, and of course, they could also do 1.25% 4 times a year. Instead of 5% once per year. So what we're describing here are different compounding frequencies. Okay, so the way we describe this is that when interest is paid once per year, this is known as annual compounding. Twice per year is known as semi-annual compounding. 4 times per year is known as quarterly compounding, et cetera, et cetera. And we can go all the way up to daily. Okay, so in other words, there's nothing to stop the bank from giving us a sliver of interest every single day. Now, interestingly enough, it turns out that in practice, if you go to a bank, like right now, when the class is over, go to a bank and ask them, and they'll tell you, in practice, banks typically pay interest every day. This is known as daily compounding. Now, that's good news for you because you're saving your money. And it turns out that, and this is the most important detail, the more frequently interest is compounded, the more compound interest the investor will earn. So as an investor or saver, you want this. You say, oh, please bank, pay me interest every single day, which is what you're hoping for. But at the same time, you might think, well, this is wonderful for everyone, isn't it? No, because here's who is not happy. This means that savers will benefit from more frequent compounding. But this also means that borrowers will pay more interest for their loans. So there's a good side to this and there's a bad side. So how do we determine what kind of interest you'll earn when compounding frequencies are changed? So in a case like this, why don't I do this? Why don't I copy this chart onto the next sheet just to see how much this will change with, let's say, something simple like semi-annual. All right, now if I'm going to do semi-annual, what I need to do is have not 20 years on my chart. Actually, let me insert one more row so it's obvious. And I might as well do that here too, so that it's crystal clear that this is meant to indicate annual compounding. That way, when you look at it later on, you won't forget what I've done. So with semi-annual, the year becomes, we're going to call these semi-annual periods, because now I need a separate row for every 6 months. And that means there's going to be 40. So instead of getting 20 interest payments for 20 years, you're getting 40 interest payments over that same time frame. Now, the only thing I have to change here, as it turns out, is the rate. Okay, 2.5%, which is expressed here as 0.025. And so, of course, it would help if I copy the formulas. Okay, now what I'd like you to notice here is that let's look at a few things. At the end of 20 years, we'll do 2 cases, annual compounding. Oh no, let's do it this way. So what I'm going to do is actually add them up. So you can see the differences. So the ending balance with annual was right here. And the ending balance here and what, uh-oh, no, something went wrong. No, that's not supposed to happen. Hold on, there's something not right. Wonder what happened. All right, let me just double check something. Oh, I know what the problem is. You know what it is? This last row is not set up correctly because this is the ending balance. This implies that there's going to be one more round of payments, which is not the case. So we'll just leave it. I didn't even notice that. So here then, Same thing. The way I've set it up, it's not, this is the last and final payment. This is the interest we earned during that last year, and to bring us to this point. So hold on one second. Okay, now it works. Okay, so that was my mistake. So the first one would be here. Oh, no. And now semi-annual is actually this number. Okay, now it's working correctly. Okay, now the total interest we can get by adding up this column. So I'll copy these numbers into here. So the sum of the interest, which is pretty clear, it must be 16. I didn't even have to copy that. It must be 1653.30 because it's just the difference between this and $1,000. Same thing down here. But let's do it anyway. It's a good double check. Okay, now the simple interest, we know what that is. All we did was we paid $50 a year for 20 years, so it's clearly 1,000. And the same thing down here, we have 40 payments of $25 each, so they have to be the same. It's the compound interest that's different. Now, I could do this in one of two ways. I could simply subtract here, or I could copy it from down below. I'll get the same results. So, for example, here it's 653.30. And down here, okay, so what I want to draw your attention to is that the ending balance is higher. Let me highlight that. The total interest is higher, and the compound interest is higher. The simple interest won't change. So the ending balance is greater. The ending balance, total interest, and compound interest are greater with semi-annual compounding than annual compounding. So as the compounding frequency increases, the ending balance, total interest, and compound interest will increase. So if I change this now, we're not going to have time to do this. If I change it to quarterly, you'll see that they all go up again and again. And if I keep going all the way to daily, they'll go up even further. The simple interest is not changing, but the compound interest is changing. It's going up, which pushes up the total interest and finally the ending balance. All right, so that was a lot of steps to go through to illustrate these principles. Turns out we have a fairly simple formula that we can use instead of going through all this work. This formula is going to tell us the ending balance of our account in the future. Okay, so once we have that information, we can figure out the rest for ourselves. All right, so in other words, this formula is telling us this number right here. Sometimes, I just want to point out, sometimes ending balance is known as the future value. You might hear that terminology, future value. So this formula that I'm about to show you is the future value formula. And you'll see some terms that we need to know. And so, what is this all about? Well, we have the future value of a sum, A. How much will be the balance of our account be in the future? P is the principal, the amount that we're either borrowing or lending. R is the rate of interest. Now, by the way, and then N is a compounding frequency. This rate of interest is expressed as an annual rate. And the time is being measured in years. But we can adjust for that. The N will actually adjust this formula for the compounding frequency. That's what its purpose is. So the R and the T are assumed to be years, but if we have semi-annual periods, that's what the N is for, to make that adjustment. Then what we have to do is make sure we understand how N works. So in other words, for example, if we have semi-annual interest payments, N is 2. If the interest is paid monthly, N is 12. And if interest is paid daily, N is 365. So that's the role of N in this formula. All right, so I think what we should do is look at an example. Yes, if you're in a finance class, yes, this will definitely be covered. So if you're interested in this stuff, you should take a finance course, and they'll definitely go over all this. The reason, you'll see why I picked this topic for this chapter, though, in a few minutes. You might be wondering what's going on here. Is this calculus or what? It is when we get to the conclusion of all of this. In other words, what I'm going to demonstrate to you is that if the interest is compounded sufficiently frequently, we end up with exponential growth. And then now that ties directly in with what we were doing earlier. Okay, so if you're finding yourself saying, wow, I want to learn more about this, then you need to go to an economics or a finance class that covers these topics. All right, let's look at this simple example. We borrow, now this time we're not the lender, we're the borrower. It doesn't make any difference. It works the same either way. We're borrowing $10,000 for 3 years. The rate of interest is 6%, but the compounding is monthly. Now we could build a chart in Excel. We don't need to do that because we have this formula. And so here the borrowers are interested, as you can imagine, in finding out how much interest he's going to end up paying during the lifetime of the loan. Okay. So first things first, the principal is $10,000. The annual rate is 6%. T, the time frame is 3 years, but N is 12 because this is monthly compounding. So all we have to do now, well, first things first, let's figure out the future value or the ending balance for this person. And if you plug in the numbers, and of course, you should put this into your calculator, you'll see that it simplifies to this expression down here. Now, this represents 0.5% per month. This represents the number of months. This, of course, is the principal. So if you take out your calculator, you'll see that your balance in 36 months, or the amount you owe or have paid, is what I should say, is $11,966.81. Now, clearly, that's more than $10,000. So that implies that you paid a bunch of interest because you borrowed money, of course. The question is how much? Okay, so here's what we're going to do. And by the way, in this question, we only want to know the total interest, but let's also figure out the other types of interest. So the principal that we started out with was $10,000. We ended up paying $11,966.81 on the loan, which implies that $1966.81 must have been our interest. Okay, that's our interest. Now, here's the big question. How much of this was simple interest and how much of this was compound interest? Well, here's what we're going to do. The simple interest uses a very simple approach to calculate it. The complex compound interest is much more involved. So what we'll do is use the following strategy. We know that total interest equals simple interest plus compound interest. Which implies that algebraically, the compound interest equals total interest minus simple interest. And that's the approach we'll take here. We're not going to have a separate formula for compound interest. It would be too messy. So this is much easier. We know what the total interest is. It's easy. We just subtract the principal. The simple interest, as you saw, is a simple formula as well. In fact, let's do this on the next slide. It can be expressed with the variables we just created as PRT, principal times rate times time. That's all there is to it. And so in this case, since we had borrowed the money for 3 years, or 36 months, I should say, we paid 0.5% worth of interest every month on a principal of $10,000. That means we were charged $1,800 for this. The interest, simple interest, was $1,800. Okay. The rest of it is compound. And so you subtract the two, and you see that what's left over, $166.81, is our compound interest. So that isn't that bad. Well, you have to do it in stages. In other words, if you notice, we did it in a particular order. We calculated the ending balance or the future value. We figured out the total interest, and then from that, we subtracted the simple interest. And so what's left is our compound interest. Now, you could probably derive a very complex formula for this, but there's really no need because it's really a very simple matter of subtracting off the variables that we do have. All right. So does everyone get what we did? Well, that's good because I'm going to give you a challenge right now to do some of these yourself. So what I'd like you to do, well, first, let me go grab that formula again. There's your formula. Now, in this example, an investor deposits $1,000 into an account for 1 year that pays an annual rate of 4%. So for now, what we want to know is what is the ending balance or future value based on these 4 assumptions about n. Okay, so remember, this first one means that n equals 1, n equals 2, n equals 12, and then n equals 365. Now, when you've got that number, you can then determine the total interest, the simple interest, and the compound interest. So why don't we do that right now? So I'm giving you a challenge right now to calculate these numbers. I don't think you'll have any trouble with it if you followed what we were doing. So why don't you take a few minutes and a piece of paper and come up with these numbers? Okay. I have to go do something in the other room for about 5 minutes anyway. So when I come back, you can ask any questions you want, but let's just get this done and we'll see how we do. All right. So I'll be right back, just a few minutes, and then we'll see how we're doing. All right. So let's see how we did for at least the first one. So those are the numbers that we'll have for all 4 cases. The principal is 1,000. The annual rate is 4%, and it's just a 1-year investment. This is a very simple example. So after 1 year, if you notice, if you plug in those numbers, now, by the way, when you're doing these formulas, your strategy probably should be to do this. Simplify it. So in other words, what I would do is reduce this number and then multiply this out before you take any further steps, so that here you can see this very scary looking expression is actually just 1.04 actually to the first power. And when you multiply that out, you end up with 1040. So in other words, in 1 year, we'll have $1,040. Very simple. So now let's decompose it into total interest, simple interest, compound interest. So clearly, the total interest is $40. That's the obvious part, because you started with 1,000, you end up with 1040, and so your total interest is 40. The simple interest, remember, is this very basic formula. Which is 1,000 times 4% times 1 year, $40. Now, that will never change throughout the rest of this problem. You don't have to keep recalculating it. And now finally, now remember, what's going on here is that you're just saying that total interest minus the simple interest that you just calculated, whatever's left over is our compound interest. And in this case, though, there is none, because after 1 year with annual compounding, there is no opportunity to earn compound interest. So here, all of the interest is simple interest. That won't last, though. When we get to the next case with semi-annual compounding, we will definitely have some compound interest. It may not be much, but it'll be more than 0. All right, so let's try the second one. Now here, the only real change is that n is now 2. So instead of 1.04, this is actually 1.02 squared now. And when you square 1.02, you get 1.0404. So look, all of a sudden, instead of 1,040, we have these extra 40 cents here. Where did that come from? Well, that's our compound interest. But let's prove it by going through all the calculations. We know already that the total interest is $40.40 because we subtract 1,000 from the future value. We already know, too, that the simple interest is $40. We've already seen that this is PRT. And like I said, this will not be affected by the compounding frequency. So all of a sudden, for the first time, we do have some compound interest. And again, yes, it's only 40 cents, but if we keep the money in there long enough, that will actually grow very quickly. This is a 1-year example. If this was a 10-year example, you'd see a lot more compound interest. All right, good. So far, so good for everyone? Excellent. Now, when we go up to monthly, yes, Fernando.
For the exponent part, when you're putting for annually, just for annually, you don't put it for the months of that, one year. You just put 1.
1 year, right? Exactly.
All right. Now I understood why my calculations were wrong. All right.
Oh, okay. Yes. So for this one, it's 2 semi-annual periods. That's why there's a 2 there. Half the interest, but twice as many payments. That's basically the way to look at it. With monthly, you've got 12 payments instead of 1. So, but each time you get a payment, it's not 4%, it's 1/12 of that. So that's basically 1 1/3%. So this basically reduces to approximately 1.00 3, 3, 3, 3, 3. These threes actually go on forever. So you can stop at some point. Keep in mind that the interest will be rounded to pennies anyway. So no matter how many digits you have, this is what you're aiming for. The 74 cents is what we're focused on. We already knew that we were going to get $40 worth of simple interest. What really was of interest was how much compound interest we're going to get. And again, it doesn't seem like a lot, but this is a very short time frame. And so, but that's still your money. You know, if you look at your bank statement and you see that extra 74 cents, you're not going to offer to give it back to the bank, are you? No, of course not. So this time, as usual, the simple interest never changed, but the compound interest went up again. And then finally, now with this one, the daily interest rate is quite small. So you just have to be a little careful with the rounding. So you've actually got here 1,000 times 1.000 1096, let's say. That's enough. And that's a lot of calculations, but that's what you get when you raise 1.0001096 to the 365th power. And so once again, you can see this last bit must be our compound interest, because we know that we started with 1,000, with $40 worth of simple interest. The rest is our compound interest. Okay, now what I'd like to do is put together a little chart here so you can see it all together in one place. Let's see. How many columns do I need? Let's start here. Now, this is one of the freaky things about PowerPoint. When you ask for a table, look what it assumes that you want. It assumes you want this weird green thing. If I want black and white, I have to go find it myself. It's so ridiculous. I don't know what they were thinking of. They didn't ask me, that's for sure. Yeah, it's in there somewhere. All right, there we are. Okay, so what I wanted to do is put together a little summary chart. All right, that'll do it. I didn't need that many columns. All right, so let me make this a little bigger so we can read it. See, when I ask for a fill, it assumes I want green. I don't know what's wrong with those people. I really don't. Green, that's what they think I want, green. Okay, so so if you recall, let's go back and read. I'm just going to throw in here the numbers that we got. So in the first case, we have 40, of which 0 was simple. Sorry, all of it was simple. and the rest was compound. Now this one I can just copy. I don't need to change this. It's the same no matter what the compounding frequency is. These are the ones that will change. All right, so let's go back. With semi-annual, 10, 40, 40, so $40.40. With monthly, this one, I left it at 704. It would actually have been, wait a minute, 74, okay. And then finally, this last one, I wrote it as 40.808. We can leave it like that, but the bank would round it to 81 cents. Okay, so this table makes it possible for you to see what's happening to our interest when we change the compounding frequency. So the total goes up, simple never changes, and compound goes up. Now, here's an interesting thing to notice though. When I went from semi-annual to monthly, I gained another 34 cents. But when I went from monthly to daily, I only gained another 6.8 cents. So what's happening here is that the amount of interest that you're earning is increasing, but at a progressively decreasing rate. So in fact, if you put all those into Excel and calculated your total interest compared with your compounding frequency, you notice it does something like this. It goes up and up and up, and then it just sort of levels off. Now, we're going to see in about a minute that there's some limiting case to this. In other words, imagine that I turn it around now and I say, what would it happen if we had interest compounded, not just every day, but every hour? And then I'd increase it to every minute and then every second. There has to be a limit to how far this can go. And so the limiting case involves what we've been studying in this chapter, which is exponential growth. The interest itself will have a limiting factor, which involves exponential growth. Now, remember what exponential growth looks like. We were shown earlier that this is what we mean by exponential growth. So if we allow ourselves to assume that interest is compounded at every instant in time, we have a special case, the limiting case of how much interest we can earn on our account, which we'll call continuous compounding. So this is the theoretical limit to how far interest can grow. Continuous compounding means interest is compounded not just every hour, every minute, every second, at every instant in time. Or think of it as interest is compounded an infinite number of times. Now, of course, in practice, it doesn't usually work this way, but it's theoretically possible that interest could accumulate at every instant in time, or in other words, we could have an infinite number of compounding periods. If that happens, then our formula will have to be very different than the one we've been using, because it would then be a case of exponential growth. So this is what we're going to use. So remember, the old formula was, let me go get it again. Here it is. So what you have to imagine is that as n increases, and I mean increases massively, and in fact, so massively that it approaches infinity, then what happens is this expression turns into this one, where remember E, as we've been seeing in this chapter, is approximately 2.71828. And again, if you remember, the function that represents exponential growth is this. And so what's happening is that this represents exponential growth in the interest that we're earning. And so that's the tie-in with this chapter, exponential growth, the interest rate. It just so happens, though, that the base is E instead of B, but it is the same thing. So this is a special case of this exponential growth function. Now, of course, you hopefully have this button on your calculator, e to the x, so you can confirm this. So imagine that we take that last case and we start with $1,000 and we put the money in the bank for 1 year and the rate is 4%, but now all of a sudden the interest is compounded continuously. Now we need this formula, and you'll see that it's not a whole lot more than the daily compounding. In fact, it's just slightly higher, which is kind of disappointing. But remember, this represents the limiting case for how much interest we can earn. So what we have here is $1,000 worth of principal, $40 worth of simple interest, and now our compound interest is right here. So that means that if we go get that chart that we had before, I can add one more row to it just to tie this together. And let me do that right here. There we go. So remember, it was $40 and 81. Let's see. 0774. Now I'm only showing all those extra digits because I want you to see how small the differences between these last two cases. So you can see it's a very small increase. And in fact, let's go get my graph back here. And I can add one more important detail to this thing, which is this line, this limiting case is continuous. Compounding. So in other words, the amount of interest we earn is limited by the case of continuous compounding. So the black curve here is never going to break through this line. It's converging towards this line, but it doesn't ever actually go above it. So that's the special case of continuous compounding. And it is an example of exponential growth. You can tell by the way the formula is written. All right. Now, like I said, in practice, you won't find any banks that are making continuously compounded interest payments. But it turns out that in finance, in a lot of formulas that involve interest rates, there are mathematical reasons why it's more convenient to use this formula rather than this one. So you might see that a mathematical formula in finance might have the continuously compounded rate. Even though it's not what's happening in the real world, you can always convert between any compounding conventions you want. So if you have a result with continuously compounded rates, you can then convert it back into any other assumption that you want. So it's a very convenient thing to be able to do to deal with continuously compounded rates. So anyway, so this is the real world example that I wanted you to see of exponential growth. All right, so only the special case of continuous compounding actually represents exponential growth. The others are close, but they're not quite there. So only this case represents exponential growth, true exponential growth. Okay, so now if you wanted to, you could go back and modify that graph. Remember way back, we created this graph. If you wanted to do one of these for continuous compounding, you would see that it goes up a little faster, the blue and the gray lines. But because it's true exponential growth. Okay. All right, so now we're obviously running up against the break time, but what we're going to see next is the opposite of continuously compounded growth. We're going to see something called continuous decay, where a value declines at this rate over time. And you might remember from high school that when you have a radioactive element, the amount of radioactivity decays over time according to this formula. So we'll save this example for after the break, and then we'll get involved with logs. Okay, so this will be our last application of exponential growth. And it's physics. Okay, that's the only example I could think of is physics, and then we can start reviewing the properties of logarithms. All right. So I hope you found this application interesting, because like I said, one day you'll have money to save, and this will affect you very greatly. All right, so let's knock it off for a while. When we get back, we'll wrap it up with continuous decay, and then we'll dive back into logarithms. All right, so see you in a bit.
Excuse me.
Yes, go ahead.
Did you post the midterm review yet?
Yes, it should be there. Let me just confirm that.
I checked yesterday. I didn't see it, so I'm just curious if you did it
Oh,
today.
I bet you didn't look in the right place. There it is.
Oh shoot.
Yeah, no, it's there. You know why? Because I tried to post some more stuff up here in this first group, and it wouldn't let me. So I figured I was out of space. I see. The thing is, the way it's set up, I'm supposed to put it week by week, and I wasn't doing that. So I changed the titles to part 1 and part 2. So yeah, just keep looking down here. If you can't find something, I would have normally tried to mix it in up here, but it wouldn't let me. So I had to stick it down here. So I guess I figured I was out of space.
Which day?
Right here. You see how it says part 2? Because yeah,
I see part 2. Hold on.
right. It's at the bottom of part 2. I was not paying attention to these dates, and so this is what
I was looking for the word midterm. That's why I missed it.
Oh no, I abbreviated it.
Yeah, I just noticed that.
Oh, okay.
Thank you.
Okay, good. All right, so let's stop for a bit, and when we get back, we'll finish up continuous decay and logarithms. All right, so we're ready for a continuous decay. Now, if you see, the only difference here with this formula and the other one, the continuous compounding, is that here the exponent is positive and here the exponent is negative. So you know what we could do? Let's see, we could get onto our favorite software package, Symbolab. And let's see if we can create two graphs like this. We'll start with y equals, oh, I don't know. How about for the positive one, we'll put 100, 1,000. Now let's see if they have E here. Yes, they do. And the exponent will be, let's say, 0.05 times 1. Okay. So when we graph it, oh boy. I guess we better look at the interactive graph. That doesn't look so hot, does it? I wonder why it doesn't look right. I'm kind of disappointed here because I know Excel could do this. All right, never mind. We'll go to Excel. And let's do this. Let's say A is 1,000. No, sorry, A is what we're solving for. P is 1,000, R is 0.05, and T is 10. So we'll have two formulas. A, well, actually, no, let's do it this way. We'll have A equals P e to the RT. And so I can make this into a superscript very easily. And then I'll do the same thing over here, but for negative, the negative exponent. Okay, based on these constants. All right, this is all I care about. So watch this. Equals B1 times E. Now in Excel, E is EXP, and the exponent is, oh, no, sorry. I have to have a column for time. Hold on 1 second. In other words, I want to show each individual year, not just once. All right, that's better. All right, so let's try that again. So it's P times EXP, and the exponent is R times T. And over here, it'll be P times EXP, and then it's minus R times T. So let's see what happens to them over time. And you can see clearly they're going in opposite directions. All right, let me just clean this up a little. Let's just show dollars and cents. And then let's graph them. All right, so let's see what we can do with this. Here we go. Now it's not, again, Excel doesn't produce necessarily very pretty graphs, but at least we can see what's going on. If we want a really beautiful graph, there are packages we can get our hands on to do this, but that's not necessary here. All we want to know is what's happening. Now, the thing is, it's hard to tell. These should be curved. Yeah, it's hard to see the curvature here. That is kind of awkward. But the blue is the one where we have exponential growth, and the orange is where we have exponential decay. So if we let this go out far enough, I guess eventually you would see the curvature. But for just 10 years, I guess that's not enough for it to show up. So I'm kind of disappointed in this graph, but at least you can see what's happening. All right, so yeah, that's all I really wanted you to see. I was hoping Symbolab could do it, but apparently not. It's just, it just, I don't know. In fact, you know what? Let me try this with Symbolab. Let me get rid of this 1,000. Maybe that's the problem. No, that doesn't, it isn't. God, what's going on with this thing? It's usually so reliable, but it's just absolutely. Oh, wait a minute. I know what the problem is. No, that's not it. Okay, well, I give up. This will do the job. Okay, very good. All right, so with the exponential decay, the only thing, like I said, that changes is you have a negative exponent. So here's a perfect example of this. High school physics. A radioactive element decays at a rate of 5% per day. In other words, 5% is converted to lead. If we start with 100 grams of this element, let's say it's uranium, how much will be radioactive after 10 days? So when you plug in the numbers, you can see, again, you start with 100. The growth rate is 5%, or the decay rate, I should say, is 5%. And this is taking place over 10 days. And so finally, after 10 days, we'll have 6.0653 grams of radioactive elements in our sample. The rest will have been converted into lead. Desmos, you think that would do a better job? All right, you know what? I've been given a good suggestion, Desmos. All right, let's see what Desmos does with this. Y equals e to the, oh boy, how do I give it an exponent? Oh boy. Well, we got off to a good start. I don't see any place where I can type what I need. Oh boy. All right, well, never mind that one.
Sure. Right below, there's like a little keypad icon. Probably try clicking that.
All right. Yeah, see, the thing is they need to make it just a little bit less obscure. You know what I mean? Like maybe somebody will notice that by mistake. How about a little label that says, here's where you put your information? That might actually be a good thing. So like here, is this thing? No, where is it?
No,
Wait, God,
right
way down
below.
there.
Yeah.
Oh, well, congratulations on hiding it so well.
Yeah.
I'm gonna notice that all the way down there. All right. Oh, now we're getting somewhere. So let's say, see, wow. Now this is very odd. It's entirely in the second quadrant. How is this possible? I don't have any negative numbers. All right, well, all right, it's fine. It's fine. I can tell, I can control exactly what Excel is doing. So I'll just stick with Excel. Anyway, so now it's time for logarithms. Now, here's an example. Now, you've seen these before. It's probably been a while. We're really not so much interested in the logs themselves, but the algebraic operations we can perform on them. So just as a quick review, if we know that y equals 1,000 or 10 to the third, then the log to base 10 is 3. So in other words, the reason why the log to base 10 of 1,000 is 3 is because 10 to the third equals 1,000. Just like when you say that 3 squared is 9. Oh, all right. I'm not sure if it's the same thing, but well, yeah, okay, maybe that's not the best example. I'll just get that out of there. But the idea here is that you're essentially rearranging this equation. In other words, if y is 10 to the third, the logarithm is essentially saying, well, whatever this number is, what is the exponent of 10 that this number is equal to? Okay, so this is the exponent of the number we have. So you can think of it as a way of finding the correct exponent. So here, for example, 10 to the third is 1,000. Let's look at a few more. So log 3, 9 is 2 because 3 squared is 9. So in other words, you're taking the 3, raising it to the second power to come up with the 9. All right. And if you haven't seen this in a while, it'll take a little getting used to, but we'll be okay. So 2 cubed is 8, which therefore implies that the log to base 2 of 8 is 3. All right. So in other words, this is simply another way of saying that 2 raised to the third power is 8. All right, you know what? Let me make up some more examples just to get a little practice. Let's say we're looking for log base 2 of 32. Well, it turns out this is equal to 5 because 2 to the 5th is 32. Or you can think of this as just when you look at this in the first place, when you don't know what the log is, let's say that you said here that log 3 of 81 is 4, or when you're first looking for it, let me do this. Suppose I said to you, here's an equation, solve for x. What you're actually being told is this: 3 is raised to x, and that gives us 81. So what you're trying to do is figure out what value of x makes this equation work. Now, your calculator should have, well, I'm not so sure about that. All calculators have the natural logs, but they don't all have the other bases for the logs. In other words, no matter what calculator you have, even the iPhone. Let's take a look at that iPhone calculator. Oh, everyone has one. I know you do. If you've never even used it, it's there. So, but make sure you turn it over on its side, because then you get a full-blown scientific calculator. It has log 10. I see that there. It has natural log, but that's all it has. I guess they figure those are the only ones you're likely to need. So, but for the others, it turns out that there are some formulas we can use to get what we need, even if the calculator doesn't have the right base. We'll see what I mean in a minute. But in this case, x equals 4, since 3 to the 4th is 81. And of course, don't forget, log base e of x is written as log x, where e, of course, is approximately 2.71828. You'll see this a lot when we're dealing with exponential growth or exponential decay. It shows up a lot in finance. So it's just written here because ln stands for natural log. You might not think that there's anything natural about this number, but it's used for a lot of purposes. So I guess that's where the name came from. All right, now, so just in the most general terms, yes, Fernando.
I just came up with maybe like a method to if you go back to the previous slide to make it a little bit more sense. Like if you look at, like, for example, log 2, 32 equals 5. I was thinking if you look at it closely, you can see that the 5, if you bring it together, 5 is like raised as the exponent.
Yes.
As below you can see. I just thought it'd probably be a simple method, maybe a little trick just to make it simple, I guess.
Yeah, whatever helps you remember it, absolutely.
Yeah, and I just wanted to mention it, I guess.
Yeah, sure. No, absolutely. Whatever helps you remember it is exactly what you should do. Just recognize that log base 2 of 32 equals 5 means that 2 to the 5th is 32. They both represent the same information. You know, it's kind of like these both tell me the same thing. All right, so the same thing is going on here. Log base 2 of 32 is 5 is equivalent to saying 2 to the 5th is 32. All right, yeah, so just do what you have to do to remember this. So these two, just in more general terms, b is the base. And of course, x is actually the exponent, but no, here y is the exponent, but yes, these two things mean the same thing. In fact, this is, let me just draw this a little better. This is a symbol that we see in math sometimes. There's actually, I might as well mention this. When you see this right arrow, it means implies. And the same thing goes, if it can go left or right. So sometimes you might have a statement like x implies y, y implies x. When you see a double arrowhead, it becomes implies and is implied by. So in other words, it's just another way of saying that these two mean the same thing. Just like with the square root case. Knowing this gives me this, and knowing this gives me this. That's what this is all about. So this is just, you know, used for symbolic logic, but it's kind of a nice shorthand to have this arrow that means implies. Okay, now one thing we do want to note about logs is that their domain is restricted to 0 up to infinity, but not including 0. The log of 0, no matter what the base is undefined. Because let's say that we discovered that the log to base b of 0 was x. That would imply that b to the x power is 0, and there is no such number where this happens. Also, I just want to mention too that the log of a fraction is negative. And you can double check this on your phone. The log of 1 is 0. And then after that, it becomes positive. The range is all the real numbers. Okay, there's no restrictions on that. But so the log function will end up looking, let's say, like something like that. Let's say that's the natural log. So you can see all the, oh, I'm sorry, I drew the wrong one. Hold on, that's not right. I goofed it up. Let's try that again. I just realized that was e to the x. What I wanted you to see this is what I wanted. So in other words, you can see down here, it falls below the axis right here. And after that, it becomes negative, but it never quite touches the horizontal axis or the vertical axis. So the range is everything, but the domain, the x's cannot ever actually equal 0. It can equal anything above 0, but not 0 itself. And that's why this picture should show you why that is. And then you can see on the vertical axis, there's no limit to the number of values of y it can have, but x can only start at slightly past 0. All right, now logarithms, common logarithms. Sometimes log base 10 is actually called a common logarithm. You may not have known that. 10 is used in a lot of applications. We're going to call this a common log. It's not a very meaningful name, but I mean, it's just saying that we're so used to dealing with powers of 10 that this is one you're likely to see in many applications. So if you hear that phrase common log or common logarithm, it just means base 10. Natural logs, as we've discussed several times, have a base of e. So it gets its own special abbreviation, log x, ln x. Now, if you do go ahead and take Calculus 1, they'll show you where e actually comes from. We're not going to do that here because it's a little too much, but just be aware, if you want to look it up in your calculator, there should be an e to the x button. And if you ask for e to the first power, you'll get 2.71828. And by the way, if you notice it goes on forever without repeating, which means that this number is irrational. Just like pi, there's no ratio that we can find that equals e to the first power. All right, now here's what we're really interested in. Here's some very basic properties that we need to know. First of all, like I started to say before, the log to any base of 1 is 0. And that's because for any b, when you raise that to the 0 power, you just get 1. Okay, and then similarly, the log to base b, like for example, I might as well throw in some examples here. The log to base 2 is 0 because 2 to the 0 is 1. Down here, we're saying the log to base 2 of 2 is 1, and that of course would be because 2 to the first is just 2. So those are the two of the standard cases. But what we're about to see is some very interesting algebraic properties of logs. They're a little different maybe than what you're expecting. All right, like what? Oh, here's an interesting one. The log to base 10 of 10 cubed is just 3. Because obviously, and oh, by the way, don't forget, this is 1,000. So therefore, what we're saying is that, and that's the reasoning. So in other words, you can think of it almost like they're canceling each other out. And now look at this disaster. The log, 10 raised to the log base 10 of, let's say, 1,000. Or let's leave it as 10 to the third power. Oh, sorry, that's not what it is. I wrote the wrong thing. Sorry, hold on. Okay, x here is 10 to the third power. Now, the reason why this is happening is because the exponent, this whole expression is just 3. As we saw right up here, log 10 of 10 cubed is 3. If you replace that exponent with a 3, you're done. Okay, so those being said, let's look at the algebraic properties. They're fun. They're not, like I said, maybe not what you remember. Maybe you do, maybe you don't. So like, here's an example. Who would have thought? The log of a product is actually equal to the sum of the individual logs. Not the product, the sum. So let's say we had log 10 of, let's say, 100 times 1,000, which is the same thing as 10 squared times 10 cubed. So you're going to call this log 10 of 10 squared plus log 10 of 10 cubed equals 5. Now, if you had wanted to, you could have done this instead. This is 100,000 which is 10 to the 5th. And so what we've just done is demonstrated why this has to be true. But this is what we're after. The log of a product is the sum of the individual logs. Oh, by the way, one more detail. These have to have the same base. All right. Let's look at some more examples. Oh, Fernando, yes.
Right there, if you want to just double check it, just like, real quick, you could just look at like log 10 within the parentheses, 100 times 1,000. That'll give you like whatever you got, right? And then
Oh,
you
yeah.
could just
Definitely. You can often approach these in different ways, just to confirm that this is correct. So in other words, you don't have to follow the rule the way it's written. Like you can just actually evaluate x times y and then apply log rules right there. But if not, sometimes it's just easier to do it this way.
Oh, okay. And you said that the base has to be the same, right?
Yes, that's right. The base has to be the same in all three cases. You can't mix and match bases, otherwise none of this works.
Oh, okay. So, all right, thank you.
Okay. So here, see what I did here? I broke it up, which clearly, because 100 equals 10 times 10, it must be the case that the log of any base of 100 equals the log of 10 plus the log of 10 again, which is equal to 1 plus 1 equals 2, as you can see down here. But you could also have noted that, oh, this is just 10 squared. So it has to be right. How about that? Oh, now let's look at this one. It's a little messier. It's not that bad. I've got 3 terms. Now, for something like this, unless we actually know the values of x and y, there's nothing we can do except leave it like this. In fact, normally you would try to avoid doing this because I think you'll all agree that this is simpler than what we've done. So without the values for x and y, you probably wouldn't bother with that expansion. You'd probably just leave it like this. Because remember, our goal is to always keep all expressions as simple as possible. One more, let's use natural logs. This could be rewritten as log 3 plus log x squared plus log y. And again, you probably don't want to do this unless you have those values, but it's certainly possible. And of course, here they all definitely have the same base as they do here. All right, so now this works both ways, by the way. If I had log of 2x plus log of 3y, I could consolidate that into log 2x times 3y, or log 6xy. And in this case, I actually am simplifying it. So in other words, when you see one of these equations, ln is natural log. Yes, ln is the shorthand. We usually see that when the base is e. By convention, we just call it ln, natural log. Because it's used in a lot of applications. But anyway, as I started to say, when you see these expressions, like here, this rule, it goes both ways. In other words, if you start with a sum, you can turn it into a product. If you start with a product, you can turn it into a sum. So that's why I wanted to throw in this example. You can see I started down here with a sum of logs, and I wanted to work it backwards into a log of a product. They mean the same thing. Now we're about to look at the quotients. Now, if a product becomes a sum, it stands to reason that a quotient becomes a difference. And that's exactly right. All right, so in other words, if I'm not multiplying but dividing, then I can convert that into a difference of logs. All right, let's see this. Okay, so in other words, here I've got log base b, all the same base. X over y becomes a difference. So in other words, log 10 this could be rewritten as log 10 of 10,000 minus log 10 of 100, which is 4 rather, minus 2, which is 2. And another option that I had here was just say, oh, wait a minute, why don't I just reduce it in the first place? 10,000 over 100 is just simply 100. And either way, I'm going to get the same number. Okay. All right, so let's look at a few more examples. And sometimes you'll not have actual numbers, but you'll have only variables. For example, how about this one? Oh, okay, well, let's see, now I've got the same base here. And what we're going to end up with is the log of this minus the log of this. It's the same thing. Or let's say we have log 10 of x plus 3 something like this. I could rewrite it now as log 10 of x plus 3 over x squared. So again, it goes both directions. All right. Now I've saved the best for last. The power rule. Now this one takes a little getting used to. If I have the log of x to the n, I can rewrite it very simply as n times log of x. So if I had, let's say, log x squared, oh, in other words, I'm going to replace or move that constant down in front of my expression, and I end up with 2 log. Down here, I've got log base 2 of x cubed, and I can simply rewrite it as 3 times log base 2 of x. So you're probably wondering why this is happening. Well, think about it this way. log x squared is log x times x. And we already know that that means I can add these up. Well, what do you know? It was that simple. So in other words, the reasoning behind this comes from the properties of the logs themselves. Since we already know that x squared equals x times x, we can convert this product into a sum, and then you see I've got 2 log x's. I can simply rewrite it as 2 log x. By the way, I just realized I'm being a little careless here with the notation. Something like this, you can write it with the parentheses if you need to. With a single constant, we often don't bother with the parentheses. But if you have something more complex, then you should probably use the parentheses. So I notice I'm being a little inconsistent here. But when you have a single value here, the parentheses are not absolutely necessary. But for more complex expressions, you probably should use them. Oh, what did I do here? Just for clarity, that's the reason, just for clarity. So in other words, if you don't, you see what can end up happening. If I write ln 3 plus x, it's not clear if I mean log 3 plus x or log 3 plus x. So for those cases, I definitely want this. But for single values, like a constant or an x or something, you don't actually need the parentheses. All right, let's look at another example of this power rule. Oh, this is where I'm demonstrating why it's true. All right, we've already done that, except with log b. Let's do an example. Here's a good one. Now remember, the square root of x is the same thing as x to the 1/2. So look what I've done. I rewrote this like this, and now it's obvious that I can rewrite this as 0.5 times log x. If I left this as a square root, it might not be quite so obvious. But that's what we end up with. And so based on that logic, we can do the same thing here. Okay, Fernando.
I'm sorry, but I can't see. Are you writing anything? Because I could still only see the previous slide.
Oh, is it frozen up or something?
Yeah, I think. I don't know.
Oh, boy. Yeah, I was writing on slide 101. Is it, I don't know, is that happening for everyone?
Yeah.
Oh boy, you know, the thing that really is bad is that I can't tell that this is happening. You'd think that it would have a way of warning me. So, okay, are you seeing the log 10 radical x yet?
No, I still can't see it.
Oh, you know, it's probably stuck. There's something wrong. And you know what? Since it's 11:30, I'll tell you what. We're almost at the end here, but we still have a ways to go. I don't want to rush through this. I'll tell you what, I'll make a note to myself. We'll stop here.
We're actually stuck on slide 97.
Yeah, same here.
The quotient rule, you mean?
Yeah.
All right, so here's what we'll do. We'll stop right here. I mean, it's 11:30 anyway. This is enough. So remember, for next time, we want to go over the sample midterm before we get back into this new material. And so we'll do that. But then when we do, I'll start all over again with the quotient rule, because now I know that you can't see what I'm doing. And we'll wrap up this discussion. And then if we have time to start 5, we're going to go back and revisit some things you've not thought about for many years, which is to say, trig functions like, you know, sines and cosines and all the rest. We won't spend that much time with it, but we want to review it because it is awfully important and it shows up in a lot of applications. So we'll spend a little time reviewing our trigonometry skills before we start something completely different. But our first priority for next week is, of course, the sample midterm. Just keep in mind, it only covers the first 3 chapters, not what we did today. And so you should have no trouble with it, but now's the time to find out if you really understand this material. And since you're doing this at home, you still have plenty of opportunity to ask questions, although it might have to be by email. Still, you know, the opportunity is there. So you'll have access to all your notes, the slides, videos, everything, and you still will have the ability to ask questions by email if you need to. So it shouldn't be too bad. Plenty of time to get it done. But first we have to do the sample midterms, who you'll tell right away, yes, I get this, no, I don't. And if I don't, I need to know right away what things I don't understand. And then, obviously find out how to fix that. So, all right, anyway, so if there's no last minute questions, I guess we will have to stop right here, whether we like it or not, because you know how technology always lets you down. It always finds a way. And today it decided to let us down, luckily, way at the end of the course, at the end of the session. So we were a little lucky today. The technology, oh, you know what I just realized? You know what I bet happened? I think I accidentally clicked on the wrong button here. I was blaming the system. Can you see it now? I know what happened. I went to move this stupid bar and I think I clicked on the wrong button. So, but in spite of that, we'll pick it up next week with the quotient rule. We don't have time to go over it now, but you can see now what I was doing. I was doing some quotient rule examples and some power rules. So I think that I will now take the blame for this. I was moving this out of the way and I accidentally clicked on pause share. All right, well, if this happens again, just immediately say something so that I can see what happened.
All right, Professor.
Okay, so we'll stop again. We'll start again here as soon as we finish the sample midterm next week. All right. So, all right. Well, that's actually a relief because that means this won't happen again. If there's something wrong with Zoom, that would be a cause for concern, but apparently not. I must have just accidentally hit this pause share button. All right. So I guess I'll just see you all next Wednesday.
All right, have a good one, Professor.
All right. See you later. Okay.
So is the midterm gonna be maybe next week, not this week?
Well, yes. In other words, what I'm going to do is when we're done reviewing, I'll post it, and then the due date will be, let's say, a week after that.
Okay, great. Thank you.
You have plenty of time. Don't worry about that. All right. Anyone else?
Professor,
Yes.
we're still good for 3 o'clock then?
Yes, I'm going to send you the invitation as soon as we're done here. It's going to come in your email, and it's just going to be a link that you can click on. It'll take you into the Zoom meeting at 3 o'clock.
Okay, sounds good.
Right. So I'll see
I'll
you
see
then.
you then. All right, bye. Thank you for class.
Okay.